Hey, how's it going? Hello, hey, Morgan, how's good to see ya? Happy Tuesday. We're gonna be doing some PyTorch. We're gonna be PyTorch experts. We're gonna be PyTorch. Oh, let me turn on the subtitles. I forgot to do that. All right, click button. All right, there we go. Subtitles are on. Good to see ya. Hey, Facecam. Hello, world. Welcome on in. Good to see ya. I figured out. So yesterday we were like rushing to figure out what the problem was with this. I think I have an idea. We're gonna try it out. We haven't asked the AIs or anything. I just thought of it overnight. It has to do with our flattening and things like that. I think we can do it. I think the decode image function that we had over here. I just opened up the terminal. I just jumped in. I think the idea is right here. So decode. Hey, thank you. Thank you for the heart. You decode right here. Wait, hold on. Decode. I'm pretty sure. Right here, yeah. Decode image. This part right here, it turns it, it changes it. It changes it. So we're gonna have to figure it out. I think we have to do something like this. Hey, Kyle, good to see you. Oh, Kyle, I can't wait. I can't wait someday until once you get 1,000. Once you get 1,000, I'm gonna jump on your live and you're gonna get a surprise. It's gonna be great. Can you try my programming language? Sure. Facecam. What programming language do you got there? Did you build your own? Did you build your own programming language? Is it in a, did you compile it to assembly? Is it interpreted? How did you build it? Or am I going off topic? Like how far am I on that? Okay, where are we here? So features 0, transform. So 100% native. Really? Native meaning that you do compile it to assembly and then you have a linker? I mean compiled. Oh, very nice. What targets do you support? And what architectures? That's a thing. We learned about this. I'm reworking user flow for Flip Profit using a VUI. Oh, hey, very nice. And you've completely optimized the item listening experience. That's great to hear. Always redoing and updating and enhancing. Kyle, I'm so excited what you're working on right now. I'm a little bit jealous actually because that's the kind of thing that I want to work on. Don't get me wrong. I've got plenty of great stuff to work on. I do. I really do. Best way to get into programming? Jump in to check us out right now. Here, what we're doing. We're learning PyTorch. We're learning PyTorch. Let's do it together. Transpiler. Oh, some transpiling. Okay, got it. All right, got it. All right, Zelby, best way to program. So I recommend watching some YouTube videos just to see what's possible. And then you want to jump into actually writing it yourself. So you have to get your fingers on the keyboard and then you're good to go. I also use the AI because when I grew up and I learned from a book, I couldn't ask the book questions. I had to just dig around for it. Just kind of dig around. So I'm kind of new to programming. Hey, no worries. It just takes here's one of my recommendations. It won't make sense. And that's okay. That's okay. It won't make sense. It'll take a while to make sense. You already know some Python? Hey, that's great. You're off to a great start. Good start. You can work on it, LOL. You can be 60% partner. Hey, there we go. Oh, that's right. That would be kind of fun. I'll have to well, maybe we'll chat more. Can you try it? Sure. I just want to see. Sir, we can try it, although we might just read through some of the code. Can you send a GitHub link or something like that? Like maybe a GitHub link? Send a GitHub link. And then on Discord. Send a GitHub link on Discord. All right, I'm pretty sure this is the thing that we need to deal with, and then we need to flatten it. Because if we put it to 0, and then we can rebatch it later. We can rebatch it. And I'd like to do that here. Flatten. Self.flatten. Self.flatten equals nn.flatten. Like that. And then we say features 0 flatten, I think. Self.flat. No, not float. Flat. I'm pretty sure. This may or may not work. I don't know. We're going to find out. Okay. I'd like to print. Well, we shouldn't print features there. We should. Okay, good. We've got it. Okay. We've got this right here. Perfect. And then we will do unsqueeze and regular shape. Perfect. I think this will give us the answer because it needs to be a one-dimensional 784 element array. Urus foundation Urus. Wait, what? Is that the GitHub link? Okay. I just want to see if my programming is portable. It might be. I don't know. We're going to find out. All right. Let me pull that up 1 second. GitHub. Let me copy and paste. This will be a trick. This will be a trick. I don't know if I can do it. Hey, quantify quantum. That's loud music, is it? I think it's pretty good music. Hold on. Testing. Okay. I could pop it down a smidge. There you go. Bop down. All right, there we go. Hey, how's it going there? I try hard. Good to see you. Happy Tuesday. We're going over to GitHub real quick. We're going to check out this right here. Did we paste that? All right. This it right here? This is it. Here we go. Urus programming language, a statically typed compiled programming language that transpiles to portable C11. Oh, very. Okay, so if you bring it over to C11 and then you compile it from there, then you can target any platform. Nice. Yeah. Hey, Torva, good to see you. Happy Tuesday. We're checking out Facecam's Urus programming language. We're just taking a look here. What do we got here? Diary, assists. What's diary? What do you got over here? Compilations? What is this? What do you got going on over here? Indonesian. What? Kantan? Oh, these are things that I don't understand. Built-in functions, string operators, compile. I understand some of the words. Some of the words I really don't understand there. Catan, English though. Stephen, have you ever tried React Native or Flutter? Yes, I have. Because I've written some SDKs for my company that were in React Native and Flutter. Check the code examples. All right, let's check the code examples. Where is that at? Examples. All right, arrays. Let's do arrays. Let's check this out. Let's zoom in, you guys. Function sum takes an array of integers and returns an integer. Oh, I like this. Okay, so it's statically typed, right? Mutable total. So you've got you have to predefine mutations. So by default, it's non-mutable. It's non-mutable by default. For I in, and you've got a range. Very nice. Total, return total. Hey, all right, I like that. Ooh, all in one right there. Looks like Rust at first glance. It kind of does. I try hard, right? It looks like a fancy version of Rust. Just like a simple version. Let numbers. Okay, so then you can assign some number literals there, a literal array, and then you can summarize. Oh, you even got. Wait, hold on. You've got format strings. You got format strings. Look at that. You're back. Had a phone call. If you tried to talk to me. Oh, Kyle. We're all good. All good. I think we got distracted by a programming language that's called Urus that Facecam built. We're just checking it out. Push items. Dynamic array. So mutate, right? Mutable array. And then you've got a non-mutable array. And you can sum them. Do you have a sum in here? Yep, you can even run sums right there in format string. Audio's fine. Nice. Good to hear. Good to hear. Thank you. Square sums. Sum the sums. Sum all the items. This is great. I like this. All right, what else do we got here? Let's look at one more example, and then we'll head back to our PyTorch there. Let's look at hello. That's an easy one. All right, let's look at another one real quick. Let's look at one more. What it would be interesting? Fibonacci. Let's check out Fibonacci. So you got some recursion in here, right? Hey, some simple recursion. There you go. What's your view on Expo for React Native? It's like the Next.js. Expo is great because it, put it on your mobile phone. It allows you to develop directly on your phone, which is great. Wouldn't you rather directly develop on your phone? And then whenever you change and make updates, it reloads the phone. It's a great developer experience. You should do it. You should make it happen. Check the spec markdown files. Okay. Spec markdown files. This will be the last thing that we look at though. In documentation maybe? Spec, you said? Security? Spec. Language specification. This must be it. Urus language specification. Data types. No value. Void. Variables. Functions. I like it. Hey, this is what I like about it. It's really clean. It's simple. I understand the syntax. It's very Python-like, except for it's got curly braces. So it's like Python with curly braces. That's what it's like. It's like Python with curly braces. And a little bit of Rust in there. and types and mandatory types. This is actually a really, so you kind of added together all the things that I kind of want in a language. You did. Immutable by default. Immutable by default. You've got, you don't have the parentheses often. You can avoid the parentheses, which is nice. So it's a little bit less syntax. You don't have any crazy brackety things, which is nice. It's clean. It's easy. Oh, you got semicolons. Okay, so you add semicolons in there. That's fine. I'm fine with semicolons. Either fine. Oh yeah, Steven, I added a Windows support and made the BTC trading bot also account for macro market news. Oh, did you? And general crypto market vulnerability. Oh, you mean variability or you mean vulnerability? Yeah, Python simplicity and Rust-like, but C fast because it transpiles down the C. Very nice. Hey, McPeace, good to see you. What are we doing today? We are building our PyTorch tutorial. We're going through PyTorch. We're going to become PyTorch experts. Let's do it together. That's the plan for today. It looks awesome. Would love to contribute to this. I try hard. Yeah, so I'll put it on Discord. I'll put it on Discord. So let's go here. I think that's it right here. All right, on Discord under link share. This was Facecam's programming language. All right, so this link share. Paste the message. There you go. Check it out. All right, do you still remember the book you used to learn in C? Yes, I do. I sure do. Computer science, although I did it when I was 11. It was called Sam's Teach Yourself C++ in 24 hours. Although it wasn't 24 hours. It definitely wasn't. Sam's Teach Yourself C++ 24 hours. All right, here we go. This was it right here. Let's go to images. Hey, that's it right there. Look at that. Wow. Actually, you know what? I think I had a later edition. This is an older one. This is an older one. I had this one. This is the edition I had. Zoom in on that. This is 11-year-old Steven right here. CD-ROM included with the compiler right there. Thanks, Steven. Yeah, you're welcome. Facecam, you're welcome. Can you link the Discord for me? Oh, the Discord. Sure, absolutely. Here you go. Let's grab that for you. Directly copy right here. Just for you. Try hard. There you go. Discord just for you. There you go. Trying to learn a low-level language like no Python. Should I go for C or C++? C is great because there's a few, right? It's few really easy. There's a few keywords to learn. There's not a lot of keywords to learn, so it's pretty easy to memorize. C is great. I think it helps you understand more of the low levels, and it gets you down. Like you go below C would be assembly essentially at that point, and below that is machine code. So yeah, that would be a good one. Thank you guys. Good to have you here. Vulnerability is in the fork. Made it separately first, but then remember, you could just fork your already existing bot instead of making a new one. Vulnerability. It's in the fork. Fork made it separately. I'm trying to figure this out, Torva. There's a vulnerability? All right, good thing I started studying C. Hey, there you go, some C. I had a question. What terminal emulator do you use? I use Ghosty. Ghosty, right here. Oh, I should type that in for you. All right, so that is Ghosty, right here. We use Ghosty, you guys. It's great because it's a GPU accelerated, right? GPU acceleration. Runs on Linux and Mac. Let me type it again more clearly. All right, sounds good. All right, you guys, I think the answer is, I think this is the answer. I'm very curious to see if this is going to work. We're going to try it. We're going to hide that, and we're going to get the sample, and we're going to print it here. I think that's it. And it's going to print the shape. Let's see if this works. All right, I don't know. I was thinking about this last night. I'm like, this got to be the solution. Is it? Is it the solution? Backside. No, it's still 28 by 28. We got to get it into not 28 by 28. That's what we got to do. We have to make it not 28 by 28. Okay. So apparently this isn't the answer. We're going to figure it out though. We're going to figure it out. So I really wanted that to be the answer. I really did. I wanted it to be the answer. The unsqueeze maybe? Unsqueeze. Let's just type unsqueeze and see what happens. Nope. Doesn't like that. Okay. Do we have this? Do 0. Okay. Let's do 0. Okay. 0. Let's try that. More clearly. Okay. This is great, you guys. Thank you for the hearts. Is it better now? Is it better? Nope, it's worse. I made it worse. That's not what you want to see. You don't want to see that. Okay. So what we need to do is we need to convert this 28 by 28 matrix into a 784, right? Calculator, right? So it's going to be 784. And we got to, I'm just going to look it up. I'm going to look it up because I don't know what. Let's see. PyTorch function that converts a 2D matrix to 1D. All right. What's the PyTorch function for this? Flatten. We could do a reshape. We could do a reshape, you guys. We could do a reshape. I forgot about that. We should and flatten. I know we did the flatten already. We tried it. It's not working. So you meant vulnerability, the vulnerability of the crypto market. Oh, the variability or like the, you know, the volatility? Are you talking about volatility? The other big four, it's in the fork of the Python bot, made a bot to account for the market and the market vulnerability. Realized you could just fork your bot instead of making another one from scratch. Hey, that's a good idea. Yeah, volatility. Okay, that makes sense. I'm like, vulnerability? What are you talking about, vulnerability? All right, now let's get into it, you guys. You would like Ghosty only available on Mac and Linux. I know, right? Although, don't you have WSL? Don't you have Windows Subsystem for Linux? Does Ghosty work on WSL? Does Ghosty work on WSL? Yeah, well, it said yes. Although it's WSL, so it's not really. You can install Linux version of Ghosty in your WSL distribution. Oh, so if you have a Windows subsystem for Linux, you can install Ghosty. Although I don't know if it's going to actually work. You do have WSL. All right, WSL with a hassle to work with. Oh, got it. Okay. I'm not familiar. I only do Linux and Mac. Hey, McPeace Mystique, thank you for saying hi. Saw you a little bit earlier today. All right, let's keep going. So flatten. Let's see if this is a feature. All right, let's do this. Features.flatten. Can we do that? Is that a function that works? We're going to find out. Is that a function? It is. It's a built-in function. It's right there. It's right there. Okay, so if that's a built-in function, let me go over here. 0. Let's see what that looks like. Let's see what that looks like. It doesn't like it. Well, time to put this PC to dual boot mode. There you go. You could also do a virtual box. You could do a virtual box. You sound like a fun person. Hey, Polish, backup, thank you. Appreciate it. We're doing fun. We're doing some fun things today. We're learning PyTorch. We're going to become PyTorch experts. Let's do it together. We're going to do it together, you guys. All right. So let's see if we can figure this out. Maybe you can do a flatten on that. Let's try that. Let's try flatten. That can work. Let's call this a flatten. Flatten. Okay, here we go. What we got? Oh, got it. I need to do dot size. I got to do dot size. Shape. There we go. Otherwise, we're gonna get a lot of output there. It's still 28. Oh no, it's right there. We did it. We did it right there. Okay, we figured it out right here, you guys. Hey, there it goes. All right, that's what we need. That's what we need. Okay, so now that we've got that, we convert it into a batch shape, I believe, or maybe. Let's see if we can get it to work, and then we can run it through our feed-forward neural network that we defined yesterday. That's it. That's what we need right there. Right there, you guys. Oh, here we go. 784 hacker mode. Yeah, you got it, love baby. Good to see you. Welcome on. It's all love baby. All right, let's do this. Hacker mode, you got it. All right, let's go. Custom data set. This one. Okay. Now that we got it in the right spot, all we have to do is say dot flatten. We don't need this because that didn't do what we wanted it to do. It didn't. It just didn't do it. Can we do dot flatten here like that? Do we just do that? We bring this back over here, delete those, and then see if we've made it. Did we get it, you guys? Did we get it? Did you update your RC files repo? I did not. Well, there's one thing that I would update with it because someone on Mastodon told me that there's a way to copy to the system buffer that I never knew about. It's built right in. Watch this. You highlight the text, you hold shift, you press double quote mark, and you press plus, and you press Y. And that puts it into your system buffer. Isn't that neat? Isn't that neat? And you can just paste it in. Repaste it. There you go. I think that's great. So I've moved over to that new format. I've moved over. Yeah, I like it. It's a lot to remember. Hold shift, press double quote, press plus, press Y to yank it into the system buffer. I like it. It's great. All right, you guys. Now that we did this, we're on the right track now. I know we're doing good. All right, let's double check that we got it right. We're gonna rerun this to make sure it looks good. Did we? Oh, no. Wait, no, we had it working. We did. Can we just do that? Okay, like that. Let's try that again. Features of shape. All right, let's try that. Maybe that's what did it right there. Oh no, we had it. We had it. No. Okay, let's bring it back. Not system buffer, clipboard. Yes, the clipboard. Exactly. Right. Okay. Which clipboard? Yeah, exactly. The system clipboard, right? So did I correct? So that allows me to, watch this. So I can copy this word right here, self.transform, shift, quote, plus copy. And then I can go over here and then I can use the system, paste. I can paste it with the paste command like that. A little bit of pasting there, you guys. So, and then if you don't want, if you want to go outside, stay inside of Vim, the Vim clipboard, you can just do the normal yank. So right here, I copied that line so I can paste it a bunch. However, it's not going to the system clipboard. All right. What do we do? How did we mess it up, you guys? How did we mess it up? What do we do? Oh, maybe here. Okay. Let's do shape. Let's close those. Label. Shape, size. Okay. Actually, you know what? Those are fine. So what did we break? We broke it, you guys. We got to fix it. Cool. Yeah, I know. Okay, let's keep going. Pretty useful if you're SSHing into Vim, though, into a virtual machine. Can you do that in a virtual machine? I know you can, in like VirtualBox, you can have it copy back to the system buffer between operating systems between the guest and host. I don't know. Yes. So if you have that configured and then you use the yank command for the system clipboard, it will then work. You have to have the VirtualBox, the VM configured for it though. Otherwise, it won't work, you guys. It'll work only for the guest operating system. All right, what do we break? Why no good no more? Where's this at? Flatten. Oh, self.flatten. Okay. Here we go. We don't want that anymore. We're not going to use this anymore. Okay. Let's get rid of that. And then we don't have this anymore. Okay. There we go. Like that. All right, let's see if we got it back now. All right, are we back? Oops, self.transform. Whoopsie doodles. We did something. Okay. Here we go. Bro, my game is in making. Time means whenever it's ready, then sure we'll share. All right, sounds good, Claude. I'm very curious about it because you've got some really good design eye there. You got. My promise is you will love it for sure because you know that I take a long time. It's going to be worth it. Well, you know what? What was it? The creator of Stardew Valley took 4.5 years or so to build the game. So if you do it in 4 years, I'll be impressed. You're probably going to go a little bit more quickly though. So what am I trying to say is you can yank text into different registers. Yes. Okay. Got it. Yes. I've only ever really needed a couple of them. And there's also the separate register right here. So I've got my tmux register, right? My tmux register. Then you've got the system register. And then I've got my vim register. So I've got 3 registers. I've never needed more than 3. Yo, the tech man, welcome on in. Good to see you. Who's that? Godson? Hey, Godson Gene, thank you for subscribing. Welcome on in. Happy Tuesday. We're becoming PyTorch experts. Let's do it, you guys. Let's be PyTorch experts. So you can manually store them in special registers and then get copied into your clipboard. Yes, there's a way to do it. I know there is a way to do it. I've never needed more than 3 though. Okay, so now we're back to the good spot. So let's jump back out. And let us go to dot flatten. Let's see that. Let's try that. Let's flatten it, you guys. Make that flat. Yeah, there we go. Look at that right there. Oh, yeah, that's right. Oh, okay, now we should be able to run it through our feed-forward neural network. I certainly do believe it'll be a lot easier now. Okay, we're not gonna have any problems anymore, right, you guys? I think not. So, bro, thank you for understanding, bro. Here is night. Oh, so good night, and sorry for leaving early. No worries, Claude. Thank you for staying up and joining in for a small bit of time. Happy to have you here. We're gonna become PyTorch experts while you go to sleep. That's the plan. How much RAM is recommended for PyTorch? You need enough to be able to do whatever size model. However, if you're doing some simple things, you don't need that much because you're only loading what you need into memory at the right time, like right here. Like we're loading in the feature one image at a time, right? One image at a time. So that means that you don't need that much memory. Me tomorrow stream sounds good. Definitely understanding with what you're saying. Hey, the tech man, that's good to hear. Sounds good. It's good feedback. That's great feedback. All right, we figured it out right there. We're trying to do flatten a whole different way, and that was the answer right there all along. Right here, you guys. The flatten right there. That's the answer. Thank you for the hearts, you guys. Appreciate it. All right, I think we're good to go. So now that we've got our right shape here, batch 64. Yep, features, labels, looking good, looking good. So I think we can start doing feed forward. This one line right here should do the trick. Right here, and we just say image, sample image, and let's print it. Let's print out the logics right there. Oh, we got to do 2 device. We'll do 2 device right there. All right. Shop HM, hey, my friend, good to see you. Happy Tuesday. We're becoming PyTorch experts. That's what we're doing now. Will this work? Okay. Now that we got it flattened in the right shape. All right. Will it work? All right, that's my question. Will this succeed? Line 95 and 96. Yes or no? I think the answer might be yes. However, you know what? It's been a whole bunch of times where we got it wrong. So if you were gonna look at the odds, the answer might be no. However, I'm feeling pretty good about this because I'll let you look at more details. So you're looking at here line 9. So let's look at a few more details, right? Let's check this out. Let's jump up here. So our model, linear, has 784, right? 784. And now that's the inputs, right? That's the inputs. And if we look over here, there you go, 784. So it's fit, it's right there, it's fit. PubNub co-founder, you got it. Astrid, Adstrix Pro, you got it. I don't understand PyTorch. Facecam, it's okay. That's actually okay. There's still many things in PyTorch I don't know either, and there's a lot to learn. The good news is, you will eventually get it. I'm almost there. We're gonna become PyTorch experts together. Let's do this. 100% yes, you guys are confident. You're really confident. I don't know. The odds are not stacked in our favor. However, I do believe that's a linear input here. We're looking good here. And if anything breaks that's not related to this line, then you still win. You still win. All right, you guys, let's try it out. Here we go. We're gonna do it. PyTorch. Is it gonna work? Is it gonna work? It worked! It worked! Look! It worked! It worked! Okay, you guys. 100% yes. Those who voted yes, you got it. It worked! It worked! I knew we'd figure it out. You knew it, Kyle. You knew it. You knew it. We figured this out. All right. That's great. Now we can actually train the model. Now we can train the model, you guys. This is successful. Hey, we did it. Look at that. Yeah. All right. So should we do 2 device here or 2 device in our, thank you for the hearts. Appreciate it. Hearts and party. What is PyTorch? PyTorch is a framework for training artificial intelligence. It's got a whole bunch of math functions baked into it, so you don't have to write your own math functions. This is the same thing that ChatGPT was originally built on PyTorch. Also, it came from Meta or Facebook. It's the open source framework for artificial intelligence. It's a really good one. It's a little more complicated than Keras and TensorFlow from Google. However, you know what? It's pretty good. You would say, instead of spending time cramming PyTorch, learn the math behind these classical machine learning models that help me easier to transfer what I learned from math to PyTorch. Yep. Mark Lemon, hey, how's it going? Good to see you, Mark Lemon. Thank you for saying hi. We did the same thing too. I try hard. We learned many years ago, more than 10 years ago, how to do this deep learning from scratch with feed-forward neural networks and back propagation, stochastic gradient descent. We did it. We learned it. Now we're trying to get to understand PyTorch. Now we're doing PyTorch, you guys. Should we do that here? All right, let's start. I've got an idea. Okay. Now that we've done the test sample, let's do the training. Def train. Let's train the model. Let's do it. Let's train the model. What's up, Soki? Good to see you, Soki. Welcome on in. Happy Tuesday. We are becoming PyTorch experts. All right, let's go to the next level. Now that we solved that problem, let's go to the next part of it. Also, I want to convert this. I want to convert this here. Oh, hey, Kyle. Member for 1 month has become the best. Steven's the best programmer. Hey, Kyle, thank you for the membership. Appreciate it. I can't wait. I can't wait, Kyle. Once you're ready, once you get 1,000, I'm going to jump over to your channel. It's going to happen. What's the data? The data is going to be fashion MNIST. This fashion MNIST. So it looks like this. Maybe I don't know. Maybe we can get this. We'd have to reshape this. Reshape, I think, to 28 by 28. I think, and then we can get that to work. Image, plot. Okay, right there. Show. Let's see if we can get this to work. It's just pictures of clothes. That's what it is. Just ate chicken salad. Hey, that sounds great, Joshua. Not the baked chicken, cheese sandwich, onions, jalapenos. Oh, okay. Now I'm hungry. Spinach topped with mayonnaise, sweet onions. I'm really hungry now, Joshua. Why are you doing this to me? Thought you were already a member. I know, that's why. Boss thank you for becoming a subscriber. I appreciate it. Happy Tuesday. We are becoming PyTorch experts, you guys, so I can train any model using company data. Well, if you want, I suppose. You might need permission. Although, I don't know. Thank you for the hearts and reactions, guys. Kyle, thank you again for becoming a member. I appreciate it. All right, you guys. Let's see here. How many of y'all are here? All right, so let's do a gift. We're gonna gift some memberships. Here we go. Let's gift some memberships. Since you guys are here right now, terms apply. Close. Okay. Wait, hold on. Send 5 now. There we go. All right, so 5 of you will get a membership. I don't know who it's gonna be. It's always random. It's always random. All right, who got it? Who got it? All right, let's take a look here. Who do we got? We got RMKR. We got, let's zoom in. All right, zooming in here. We got Papa. We got Papa Owl. Maniharanarchy. And Green Balls. You all got some memberships there. You got some gifted memberships. Congratulations, you guys. Hope you enjoy getting all the party. Yep, thank you for the party poppers. Appreciate it. And all the 100s. Let's go back to 0 and zoom in on that. There we go. Yeah, good to have you guys here. That was an error. Been member. Oh, it was free chat. It was the whole time. Hey, all right. Sounds good to me. 0, 0, 0. All right, you guys. Y'all are members now. Y'all are members. All right. You can drop the neurons. You can drop neurons in order to stop overfitting. Yes. Mostly, yeah, that's one of the ways to prevent overfitting. What you want to generalize your model so that way it's able to predict on data that is never seen before. That's what the whole point of AI is training, is that you train it on a whole bunch of data, and then you give it new data that it's never seen before, and it can give accurate predictions. That's the whole point. That was an error. No, just that once. Okay, because you hit a member milestone. Oh, got it. It's a YouTube feature. Really? Oh, I didn't even know about that. That's great. We're learning new things, you guys. We're learning new things every day. All right, let's keep going. I'm the only one who is really exhausted today. Jin Lu, hey, good to see you. Welcome on in. Well, it's time to relax. It's time to relax, Jin Lu. All right, I think we can do a shape here. I think we can do a shape. Let's do that. Oh, whoa, Kyle. You sent 5 memberships. What do you know? Look at that. More members. Hey, what do you do? All right, so now I've lost count. I think we're what, like a 5, 10, 15, 16 now? You did 16? I'm keeping track. We got Josh, Doka. We got Daco, Your Q, Anonymous and Green Bean. Hey, very nice. Y'all got subscribes. Or well, you got memberships, you guys. Thank you, Kyle. Whoa, Kyle. You get up to 1,000, Kyle. I need to reciprocate. Don't gamble, Kyle. Fam, yeah. GG, Kyle. Yeah, Dak Dog 320. GG, Kyle. Let's see if we can pull up the image. Let's see if that works. Or is it gonna crash? Here we go. All right, little syntax challenges there. Like that, okay. All right, did we get it? We reshaped it. Model to out. Okay, problem. Where's that at? Out. Where's that? Out? That should be fine. Why is that a problem? Hold on. PLT. Let's just hide that real quick and double check that we didn't mess anything up. Yeah, we did. We messed something up. Where did we mess it up? Hold on. Wait. What do we do? How do we mess it up? All right, let's just undo some things here. Let's undo a few things. This should be fine right here. Okay, let's run that. That should be fine. What is the deal? It was just working. It was. I swear. It cannot access local variable out where it was not assigned. Oh, okay. Well, what happened? Here, let's redo this. Let's just bring everything back. Forward out. Oh. Batch. Okay. Okay. We should simplify this. Tomorrow I'll start financial analysis job. Really? I still haven't decided if I'm going to use Python or Power BI. I don't know, right? Microsoft or open source. Kyle, thank you again for the memberships. That was fantastic. I was not expecting that. Did we break it? Okay, good. There we go. That's what I'm looking for right there. Okay. No worries. Thank you. Yeah, that's great. Okay. So we could just do this. Here, let's just do this. You know what? We'll leave it for now because we might need it later. Oh, we're just going to go return to simplify it. Okay, our forward pass function looks a lot easier to deal with now. Double check that's still working. All right, now let's bring back our print so we can show the data that we're looking at. Hey, I knew. All right, perfect. So this is a jacket. That's a jacket. So this is a sample of the data that we're currently looking at right here. So we're going to train our model to learn different clothings. That's what we're going to do. Join Discord. Yeah, there you go. Join the Discord, you guys. Thank you, Kyle. Okay, so let's close that off. And let's train the model. So that's the plan for today. We've got one objective. We're going to train the model. Okay. So we did that. We did model, blah, blah, blah. All right. Rand. We don't need to do randoms. We already got the locates. So predicted, we could do a softmax on dimension 1 on the output. You don't need to do softmax. It's just nice. You only need to grab the argmax to really get the answer. Let's see, argmax. You don't need to do softmax. Why is it doing that? This is weird right here. You don't need to do that. It's doing something it doesn't need to do. The tutorial's broken. Right there, look. The tutorial's broken. You don't need to do that. Softmax is just a really nice transform that scales up the probabilities, but you still grab the first arg. It's still going to be argmax. It's still going to give you the same answer, whether you do it or not. I think there's something weird going on there. Look at that. Okay, so watch this. We're going to show you that this is how it works. Okay, so thank you for the hearts, you guys. Appreciate it. I'm going to hide that because we don't need that anymore. And we're going to say the argmax. How do we say argmax equals the logits? And that will be dot argmax. I think we should say dot argmax straight up like that, right? Dot argmax. Like that. And we'll print it. Print argmax. Okay, so f string the argmax is going to be a argmax. Oh, I suppose we could just do that. Okay. We don't need this. Okay. So we just do this right here. I'm pretty sure that'll work. Let's find out. Did Steven get it right? Hold on. Wait. double check that we didn't mess anything else up. Okay, that looks good. Okay, so our tensor output right here. Let's do argmax on 0 maybe. All right, let's try this. Hey, see, I told ya. Yeah, okay, double checking that this is the biggest one. Yeah, it's 9. You get a -1, and they're all -8. Okay, yep, nothing better. So yeah, this got it right. See, I told you, you don't need to do this right here. Why'd they do that right there? Look, in the tutorial, they're like, you gotta use softmax. Nope, that's just a waste. It's a pure waste. It's a straight up waste right there. Predictions, the predicted class. So what we need to do is we're gonna print out what we think the prediction is, and then we'll show it. We'll do everything all in once. It's gonna get it wrong, which is fine. We don't need to worry about that. So we'll grab the argmax and we'll say print F, and this will be, what is our labels? Okay, we got our labels, and we got our label map. Label map. Let's do this. We need it to be in the, I think we just do label array. I think we'll just grab label array. Or do that. Label array. Okay. Label array. Argmax. Like that. That's it. Equal sign. Is that gonna work? I don't know. We're gonna find out. We're gonna find out if that works. This will work. I'm pretty sure this will work. Here we go. And it didn't. Why not? Wait, why didn't it work? Why is that not happy? Hindi video. Oh, there it goes. All right, it just didn't work. All right, so it thinks that's address. It's not address because we didn't train it yet. It's not address because we didn't train it yet, but it thinks it's address, which means it did work. Hey, thank you for the hearts, you guys. Humo Comedy 1. Hindi video viral kur do? What? Are you speaking English? I don't think so. Okay, so let's go ahead and hide that. Now that we did the test sample, let's do the training. This is the one plan for today. All right, model layers, don't need it. Input image size. We already got our data. We don't need to worry about that. We did our flatten. We flattened it. Hey, we flattened it pretty good. I've been trained. It's a purse. You did. You should have been trained. Why PyTorch instead of Jax? Dak dog. Well, I don't know. I've never tried Jax. That's why. I thought PyTorch was the good one. Jax AI training. Framework. There we go. Jax. Maybe we should be doing Jax, you guys, this whole time. Matplotlib. Wait, why are you having... Oh, JNumpy. All right, Jax NumPy. Let's make the screen so easier to see. Let's take a look, you guys. All right, we're maybe changing our mind. It looks like NumPy, except for... All right, Jax array. How do we do deep learning with Jax? All close. So we're gonna have to learn a whole bunch of new methods. Norm X block until ready. Okay. So Jax versus PyTorch. Let's take a look, you guys. All right. PyTorch and Jax are both powerful deep learning frameworks that differ primarily in their programming paradigms and target use cases. PyTorch is an industry standard object-oriented framework known for the ease of large-scale ecosystems, while Jax is a high-performance library with a functional approach, excelling in research and large-scale It's the same thing! It's the same thing. Object-oriented function versus functional. Generally considered easier, has a steeper learning curve due to its functional nature. I'm fine with functional. I like functional programming. I'm perfectly fine with that. I like functional programming. Please keep your messages in English. Yeah. Fast performance, faster in specific scenarios, especially with JIT compilation on Google's TPUs. Okay, so we don't have TPUs. We do not have those TPUs. Large, more mature, smaller, rapidly growing. Yeah, it's newer. Dynamic graphs. Debugging can be more complex. Robust. Lacks built-in polish. Okay, so we're using PyTorch right now. Maybe we'll do Jax later. Okay, I don't mean to sidetrack you. Just curious. Me too. Me too. We're learning together. That's what we're doing. Part of becoming a PyTorch expert means that you should also know what else is available on the market. Right? It does mean that. It does that mean... All right, old McDonald. Change that up there. Okay. Let's train it. Let's train it, you guys. Let's train. Let's do the training. Let's make it happen. All right, let's get rid of our prints because we don't need this anymore. Where is this at? All right, we don't need this. Let's get rid of that. And we don't need to run test samples anymore. Let's just close that off. Make sure we're good to go. Nothing else is printing other than the model. Okay, looking good there. Looking good. All right. Oh, TPU. Yeah, I looked into that once. Google Tensor Processing Unit. Thought about maybe buying a... Whoa, Tensor Torrent? Wormhole TPU. Performance is currently just a bit more efficient than normal GPUs. That sounds pretty great. You can buy a hardware accelerator specifically for AI. Good info and during the stream. Thank you, Dak Dog. Appreciate you joining in and giving us some information because we're learning together. Hey, some random coder, what happened to the 1 million divs? We did it. We made it work. I thought the browser was going to crash or it was going to give you like one of those JavaScript warnings like this page is running too long. Would you like to exit the page? When you know those warnings that pops up on that screen, it's like you cannot. Would you like to continue running this page? It's running a little bit slow. We avoided that completely and we added 1 million divs successfully. We did it. It worked. Thank you for the hearts, you guys, and reactions. Appreciate it. All right, let's keep going. So let's get into the training. We're gonna do some training now, you guys. Let's do the training part. Okay. We don't need to worry about that because we've already done that part. We know what the ReLU is, right? We're getting details, right? So this will be the before and after on the ReLU. Gets a whole bunch of zeros in there. Great for dropout. So this actually kind of helps from a dropout perspective. We don't really need dropout if we're using ReLU. We don't. Why would you need it? I mean, suppose you still could, right? You still could. Here's a sequential model. La la la. The output. Easy, simple. See, this is what I wanted to do. I wanted the flatten to be right here. Whenever that happened, it never worked. It didn't work the way I wanted it to. So you can do softmax if you want. There's no reason to unless you want to look at all the probabilities together, right? So softmax is nice from that perspective. So let's actually take a look at softmax really quick. So I think it's pretty neat. So this is argmax, and let's do a softmax. We'll do a softmax here. Softmax equals, it is nn.softmax. We'll go the logits, and we will print softmax. I think. Let's see what that looks like. See if that works. Did we get it right? We did get it right. Yeah, see, so this is what softmax looks like. Is that what that looks like? No, that's not what that looks like. That's wrong. Softmax is down here. There it is. Okay. I was gonna say, I'm like, wait, so softmax, so this is what the, what the output is, right? This is the output. Where the output is. Let's not do, here. We have the logits here. Okay. Like this. So it's prettier so we can see what's going on the screen. Okay. And then rerun. Okay. Warning, implicit dimension choice for softmax has been deprecated. Change the call to include a dimension argument. 0. There, fine. We did it right there. Perfect. Okay. So here's the output on the standard logits right here. So you can see it's got very, very small numbers. Very small numbers. And one very big number. Or a standard number, right? Right there. Very big number. A whole bunch of small numbers. And when you softmax it, it changed that distribution probability so you can see what each value looks like. So this is 15%. And you can see that's one of the highest, right? 15.87%. This one is 5%. This one's 15.8. So you can see how there's a bunch of different probabilities in there. And it kind of lets you run a understanding about which is the model thinking that the current image is going to be. Is it a picture of a boot? Is it a picture of a shirt? Hey, how's it going there? Ayush, wait. Ayush, good to see you. Ayush, welcome on in. Let's keep going, you guys. So let's train it. Let's train it up. Okay. Model parameters. So we could investigate the model parameters if we want. See if you're going to draft tech specs and go to market strategy document for flip profit. If you could give me them a once over. All right, that sounds good. We'll do it. We'll do it, Kyle. We'll do it. Absolutely. We'll check the Discord direct messages. Oh, yeah, TPU looked into that once. Okay. And you said because they convert the model from NVIDIA Google systems to the hardware like a TT Metaluum? What? And then the model performance gets lost in translation. So even it has a nearly 5x hardware performance, and the real difference is like only a 1% difference. Okay. Haven't sent it yet. All right, Kyle. We'll be ready to look out for it. All right. So let's do training. Wait, I wanted to do training. So we haven't even gotten to the training part yet. We're just looking through. So this is exploring the model itself. Okay. Hey, see right there. That's what you want right there. That's what you like right there. That's what you like right there. I like it. Okay. So I wonder if we could convert it to be a sequential model with flatten. Although I'm not sure. Hey, bro boy, good to see you. Welcome on in. Hi, good to see you. Happy Tuesday. We're becoming PyTorch experts, you guys. Where is the training? All right, so what is this? Automatic differentiation with Torch Autograd. When training neural networks, the most frequently used algorithm is backpropagation. Yeah, all right, yeah, exactly, that's the one. In algorithm parameters, model weights are adjusted according to the gradient of the loss function respective to the given parameter. You get the data from the output. You track the loss compared to the actual answer. What are we doing? We're becoming PyTorch experts. Let's do it. We're going through all the PyTorch tutorials, and we're learning PyTorch together. That's what we're doing. Input parameters X, W and B for weights and biases lost in the function. Can be defined in PyTorch in the following manner. Oh, right. Okay. And then you create a loss function. Binary cross entropy with logits. Okay. I think that's the loss function that we're going to want. Right there. That's the loss function that we need. We're going to need that one. This is actually computing the loss directly, though. X times the input. X times input of the, right? X times, which is the input, times the parameters, which is the weight or the brains, right? The intelligence of the model. And then you add in the bias. And it gets you the output. Z? Usually this is Y. Oh, is this going, what is Z in this case? Does it say what Z is? Oh, it's the result of the matrix multiplication. Got it. Okay. And then it becomes CE somehow. I don't know what this is. What is CE? CE. Is that in here? Does that... They just have CE here, which is the Y. I mean, they could just go ZY, or it could just be Y. Why this extra step here? What are we doing? Cross entropy. Oh, cross entropy. All right, well, cross entropy is the better one. Okay. Binary cross entropy. That's the one. Good. Thank you for mentioning it, you guys. Thank you. We'll be using that loss function. You can set requires grad when creating a tensor later by require grad true. Okay. Gradient function. Gradient function for means what? That's what it means. Oh, got it. Exactly. Okay. All right. Sure. Oh, it's what this part is. Okay. Got it. Okay. Cross entropy is CE. That only took me a good second there to know what you mean. Cross entropy. Right here, you guys. Cross entropy. Okay. Why should or should not I do PhD? Well, if you can get a job in industry that typically takes you farther, it really depends on what your goals or outcomes. What's your ambitions? What are you striving for? Do you want to become a teacher? A PhD might be a good idea. Are you going to go into AI field? PhD might work. Otherwise, there's no need for a PhD. There's not. You don't need a PhD, I don't think. I don't think so. It's better to go into industry. I think it's better to go straight into industry, which means you get a job, right? You compare the output of the linear operation and your labels to get the loss using cross entropy. Nice. Okay. That makes sense. Got it. And then this is the actual loss. Okay. So this is the loss function. So we got CE, which is the loss function. And so this is the part that's confusing because you get Z and Y in here, which is odd because this is usually Y right here. You got Y and you throw that over to cross entropy and that gets you the loss. Perfectly fine to me. Perfectly fine to me. It's just, those are your inputs. Oh, right. That makes sense, right? Input to the CE. Oh, wait, there's two inputs, Y and Z. Oh, right. Y is the answer. It's the labels. It's the labels. Got it. So Y and Z right here. All right, so this is the output. This is the actual output, right? And then Y is the labels, the actual answers. Z is the result from the feed forward. And loss, the cross entropy. We got it now. We're figuring it out. Okay. It's like my brain doesn't think in this form. I just don't think like that. Yeah, I don't know why they call it Z. I guess they got to call it something. We're learning together, you guys. Thank you for helping me. Thank you for helping me. This is great. Gradient function for Z. Gradient function for loss. Loss to gradient function. Okay. Gradients. Then gradient, which allows you to then back propagate. So you compute the gradients, which is the upstream loss, right? So you upstream calculate the loss of every single gradient, and then you go back and you can back propagate, optimize. You can optimize with applying the loss of each of the gradients to the layers in your weights, right? You can do that, and there you go. And then you're training the model. Obviously, you apply a learning rate. Why the music? We could go to the next song. How about that one? That one's a little bit better. Okay. Disabling gradient tracking. You want to do that for... By default, all tensors with GradTrue are tracking their computational history and support gradient computation. However, there are some cases where you don't need to do that. For example, when you already have a trained model and just want to apply some input data, we only want to do forward computation to the network because we're not going to do any back propagation, which is usually what you mean when you don't want to do training because you're doing inferencing. We can stop tracking computations by surrounding our computation code with Torch NoGrad. With Torch NoGrad, we'll automatically turn off all the gradients. Okay, good to know. So that allows us to do inferencing, and it's faster. And then a way to achieve the same result is to use detach method on the tensor. Oh, all right. Hey, Domalier, good to see you. Welcome on in. Happy Tuesday. Can you go further into the inferencing versus retraining? So there's multiple are you talking about retraining? Or there's kind of different approaches you can take there. So you've got already an existing model and you want to fine tune it. You can do it in multiple ways. You can either unlock every single layer and continue the training process by adding in new data to it, adding new data, train the entire model, or you can add more layers onto the end and retrain it. So you can increase your batch size. Not only faster, you can also fit more in memory. Oh, so you can, got it. Okay, that's great. We're learning new things. That's awesome. Well, I mean, back propagation versus inferencing. Oh, okay. So with back propagation, you're just calculating the loss across each of your layers. So we've got a bunch of layers here in our model, right? So you got a bunch of layers here. We got another layer right here. Right here. Let me pull this up there. So you got, there we go. So see, we got a layer there, and then we got another layer right here. So I've highlighted all the layers we got right here. So when we push data through the model, that's a feed forward, and that's technically the inference, right? That's the inference. And then the back propagation part is when you get the output and you have the real answer and you compare the real answer. So you've got your answer and you've got your predicted answer, which the model gives the output, and you subtract these two, right? And that's going to equal the loss. Essentially, right? You might put some more stuff around this, right? So you might have a few more, you might have like right cross entropy loss. You might do that. The very basic is just a subtraction like that. So you can see how wrong the model was. This gets you the loss. Then you take the loss and then you take, instead of going forward in the model where you take data down through the model and you calculate the answer, you take the loss and you calculate in reverse. You go up the model, which backwards, right? Backwards through the model. Every layer, you calculate the gradient. It's called the gradient, which is just the invert of, or the difference. I call it the difference. And then you take that loss for each layer. So you say loss 1, right? And then you've got another loss 2, loss 3, right? And then you apply these losses with the learning rate onto each of these models. So you subtract, sort of like subtract equals times learning rate, like that. And then it updates the layers, and that's the intelligence that you learn. That's how the model learns. That's back propagation. And then forward propagation is just without that step, without the back propagation. That's it. What really funny that you don't actually have to go from the back. You can go from the front to calculate the gradient. It's just more efficient using usually to go from the back. You can do it forward. I've never done it forward before. I've written in my own. I've never gone forward. How do you do that? I suppose you've got the output. Don't you need to calculate every single layer backward? Though, don't you need the I know you can do it the way you're describing it. Aren't you losing information though? Thanks, Steven. Yeah, see if we got some explanations there. Get things going. Depends on how many inputs and how many output layers you have. Oh, got it. Okay. Got it. So what if you're using like a convolutional neural network or a transformer where you've got filter layers, right? You've got QKB. You've got like, it's not a sequential model. You've got a Q layer, a key layer, and a value layer. These are the filters, and they're each of their own layers, right? So wouldn't you need to calculate this layer and then apply them directly? You'd need the value of this one first before you can calculate the gradient loss for these upper layers. I think, right? I'm pretty sure. All right. Let's make sure we didn't break anything, because usually we do. Okay, we're good. Okay. So I think we did a pretty good job at going over this page right here and understanding like what's going on here. Disable gradient tracking, back propagation, detaching, which is just taking it away from the graph, right? So in TensorFlow, and probably PyTorch as well, the graph is connected across every single one of your layers in every single step. It's tracked separately along all the different functions that you use in your PyTorch model. Also, everything that happens outside of your model as well in the connected graph. When you use detach, it's actually going to pull that result outside of that graph and allows you to create maybe another graph or just use the results of the data. I don't think it should influence it. You still have all information. It's just how you do the calculations. If you look at the pure math, you get the gradient of both. The thing is that for each input, you need to calculate it. I don't remember 100%. Okay, got it. Understood. So you can do the way you're describing. I'm pretty sure all you need is the initial output loss, and then you can take that loss and reapply it to all the different gradients. I'm pretty sure you can do that. I'm pretty sure you can. And it will learn and it will train. I'm not sure because every layer I thought depended on every prior layer when you're recalculating the back propagation, because you're doing subtractions for the loss. And every gradient is then passed into the next calculation for the next gradient. You lose accuracy. Yeah, so you can do it the way you're talking, and I've done it that way before because it's actually kind of surprising how forgiving a neural network can be. It really is. You can build one and it will work, but you can lose accuracy. The chain rule. Oh, is that a rule? Is that actually a thing? The NitroPython. Tell us about the chain rule. We could go look it up. We could go look it up. Just tell us about the chain rule. Shiva, good to see you. Welcome on in. Good to have you here. Good to have you here. All right. Tell us about the chain rule. No, I'm back prop. You need the previous. To get the gradient, you don't need it. Oh, okay. Interesting. I would need to... I've only built it a few times, which should be more than enough, you'd think. However, it is kind of complicated, so it's pretty easy to forget. Chain is related to the derivatives and the backpropagation. Got it. Okay, so right. So when you're calculating a derivative like a tangent or a ReLU derivative or sigmoid derivative, PyTorch is used to program a fire source on stick like a literal torch. I don't know, what is PyTorch? NFD, good to see you. Welcome on in. Happy Tuesday. We're learning PyTorch together. We're going to become PyTorch experts. Let's do it, you guys. And since you have the gradients, you don't lose accuracy. Oh. We'll have to get back to that. Good morning. Holding an all-nighter. Hey, DWSP, good to see you. Good all-nighter. Torch doesn't support this as far as you know. Okay, that's fine. We're just going to follow the PyTorch approach. It's tied to the computational graph stuff you're looking at. It sure is. We're tying all the computation. Oh, more on computational graphs. Hey, the chain rule. Hey, look at that. It's right there on the screen. Let's read the screen, shall we, you guys? Conceptually, Autograd keeps record of data tensors and all executed operations along with resulting new tensors in a directed acyclical graph consisting of function objects. In the DAG, leaves are the input tensors. Roots are the output tensors. By tracing this graph roots to leaves, you can automatically compute the gradients using the chain rule. Hey, look at this. We're talking about it right now. Isn't that great? Pulled an all-nighter. No worries. All good. Got your coffee. Was actually trying to download PyTorch through my command prompt on my computer yesterday. For some reason, though, couldn't find the correct path to find it. Well, it is kind of tricky to install because it's got some dependencies. It sure does. Let's read about it, guys. In a forward pass, Autograd does two things simultaneously. Run the requested operation to compute the resulting tensor, which we got. Maintain the operation's gradient function in the DAG, directed acyclic graph. Directed acyclic graph. The backward pass kicks off when .backward is called on the DAG root. Autograd then computes the gradients, accumulates them in respective tensors, using the chain rule, propagates all the way to the leaf tensors at the big top of the tree, down the bottom tree. Okay. DAGs are dynamic in PyTorch. An important thing to note is that the graph is recreated from scratch after each backward pass. Autograd calls populating a new graph every time. This is exactly what allows you to use control flow statements in your model. You can change the shape, size, and operations at every iteration if you need to. Because it keeps track of it, you guys. It keeps track of it. That sounds pretty great to me. All right, now we got some math here. Optional reading. Okay, skip it. Although if we're becoming experts, we should probably read the optional reading, right? All right, so I'm pretty sure we're not going to get to training the model today because we're getting through a lot of stuff here. Optimizing the model parameters. This is the training part. So maybe. All right, let's read the optional reading. We're going to be good students. We're going to be good students, and we're going to do the optional part. Let's do it, you guys. Do you provide the link you were using? All right, yeah, I'll throw it here on Discord under link share, you guys. There you go. Discord on link share. This is where we're currently at. Okay, let's do a different song, please. Thank you. Okay. Optional reading. In many cases, we have scalar loss functions. We sure do. And we need to compute the gradient with respect to some parameters. However, there are cases when the output function is an arbitrary tensor. In this case, PyTorch allows you to compute the so-called Jacobian product. The Jacobian product. And not the actual gradient. I don't know if we need a Jacobian product, you guys. I don't know. I'm still nowhere near able to use PyTorch. You're downloading ahead of time only because you're trying to prepare everything for future learning processes. Although, after you kind of realized you did, Jacobian. Jacobian. Is it Jacobian with the O? So extra O's in there, Jacobian, or is it Jacobian? PyTorch is technically a neural network for creating that stuff. Still nowhere near that. Oh, definitely looking forward to learning it. Nice. As far as you know, YouTube livers only speak and interact with audience, but not as you do with the audience using the live captions. Hey, thank you, love you. Hey, Shiva, thank you, Shiva, her, I appreciate it. That's really great feedback. Do you provide the link? Are you using? Yes, in the Discord, right here. And the link to the Discord, if you want, will be right here. Here you go. All right, so at Michael, at M-I-C-H, here's the link to Discord. Right there, just for you, Michael. Thank you for the hearts, you guys, appreciate it. We're doing the optional part. We're learning about Jacobian products, which, do you need it? Do you need a Jacobian product? I don't think you do. We're gonna find out though. I'm pretty sure I've never used this, and I've used a lot of AI. In many cases, we have scalar loss functions and we need to compute the gradient with respect to some parameters. However, there are cases when the output function is an arbitrary tensor. Yeah, isn't that always the case? Isn't that always the case? I thought it was. You looked it up with the method I've mentioned, and you can do it in PyTorch tools. It's called forward mode auto diff. There is a way to do it. Hey, that's great. We're learning new things. Forward mode auto diff. All right. Steven, do you have an AI that interacts with your chats? I currently do not. Yes, I do. There is an AI moderator. So there's an AI moderator. If you chat something in the chat and the moderator says no, it's not classroom safe, then it will block you. Do you have a GitHub so we can help make some big business together? Hey, with the interns. I do have a GitHub. I do. My GitHub is right here. Here's my GitHub, you guys. Let's see here. Is that here? No, this here. Hey, let's pin this tab real quick. There you go. Here's my GitHub, you guys. Right here. Here's my GitHub. I'll also post this over here onto our Discord, you guys. I'll post this on Discord. Right there under link share. The link share channel in Discord, you guys. All right. So we got about 20 minutes. We're doing good. We got about 20 minutes. I think everything's fine. We're looking good, guys. We're on the right track. About 20 minutes to go. Okay, let's do this. So, let us keep reading. Let's keep reading. The Jacobian product. PyTorch allows you to compute the so-called Jacobian product and not the actual gradient. Okay. 20 minutes? I know. 25 minutes. Yeah, got it. Yeah, exactly, Kyle. And sneak in an extra 5 minutes there. Sneak in extra 5 minutes. For a vector function y, blah, 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 where x and some parameters, x is a whole bunch of different features, y is a whole bunch of different labels, right? An array of labels, array of features, right? So like a photograph with pixels, and then a classification, which is, are the pixels a cat or a dog, right? A gradient of y with respect to x is given by Jacobian matrix. All right, so that looks like matrix multiplication to me with a division. Okay, so y1 over x1. Interesting. I've never needed this before. I've never used this. I don't know what this is. That extra 5 minutes adds up after a few hundred streams. It sure will. It sure will. All right, did we hit the end? Oh, we did. Okay, let's start over here. Let's get this going here. We'll go to that one. Okay, yeah, we'll do this song. This song's fine. Okay, instead of computing the Jacobian matrix itself, PyTorch allows you to compute the Jacobian product. For a given input vector, This is achieved by calling backward with v as an argument. V, okay, the size of v should be the same as the size of the original tensor with respect to which we want to compute the product. You know, it certainly would be nice if they used a little bit more friendly language in here, because they're using a lot of heavier math terms. I understand what's going on. It's just that it makes it difficult for me to sort of describe it. All right, so let's read through this. We know this. So torch.I is going to create a new matrix with a 5 by 4 matrix. Includes gradients, and then we're going to add 1 to it, double it, or well, power of 2 of it, right? So double it, right? Or double it, and then transpose. So it's going to look like this: 4, 4, 4, 4, 4 in diagonal with a bunch of 2s, and then the second tensor doubled, right? Yeah, doubled it right there. See, I told you, doubling it. And then you're going to do backward 1s, retain graph. And that will be is this the Jacobian product right there? Calling after zeroing gradients. It returns it back. Interesting. Backward, 1s out, retrain. Call after, okay. Zero the gradient. Yeah, we don't care about that. Okay. Notice how, you have the Discord, right? If you would be a great community to be able to learn more stuff. Yeah, for more people who are more educated than me. Let's do it together. Let's see. I think that's a good idea. DWSP, great idea. You've got a great idea there. Notice that when we call the backward for the second time, the same argument we did. Backward, but we cleared the gradient out. It gave us the original, right? Okay, so first call, print first call, print second call, and then print call after zeroing out the gradients. It seems to have removed this. It seems to have removed this operation. The value of the computed gradient is the gradient property of all the leaf nodes of the computational graph. If you want to compute the proper gradient, you need to zero out the gradient before in real life, what? An optimizer helps to do this automatically for us. Previously, we were calling backward function without parameters. It's essentially equivalent to calling with a tensor of 1. Oh, right. Oh, so which is a useful way to compute the gradient in case of a scalar value, such as loss during a neural network training, when you get one scalar output. When the output is a binary, 1 or 0, instead of an array. That's interesting. Learn to send text for this. It seems very familiar. Looking at the send text, I'll call it a good sign. Sending text? All right. Making our way with sending text. I'm not exactly sure what you mean. Are you typing in the chat? What are you talking about sending text? Basically, you accumulate them. If you don't zero them out or the S like that, always remember to zero out the gradient. Okay, so that's the story. Always remember to zero out the gradient. Remember to zero your gradients, you guys. That's what you got to do. Got to zero out the gradients. Otherwise, problems will happen, right? If you don't do it, problems will happen otherwise. Kyle with extra 5 minutes, still 20 minutes left. I know, right? 10 minutes. We got 10 minutes. Don't worry. We've got time. All right. So we read through that. We understand it. We didn't write any code for this, which is okay. I think we're fine. I'm feeling a little uneasy about not writing code for going through this one, although there was not much code for there to be. So let's go over. We're going to start. So tomorrow we're training the model. Today, let's little sneak peek. Let's do a little sneak peek of tomorrow. Which developer are you? Hey, Harsh, what do you mean? Which developer are you? Which developer are you? Tell me about you. What does that mean? Answer. Oh, what? You want the question? What kind of answer are you looking for? Okay. Now that we have a model, data is time to train, validate, and test our model by optimizing its parameters on our data training model. In its iterative process, each iteration of the model makes a guess about the output. This is what the model thinks the answer is, right? Is it a shirt? Is it an ankle boot? Who knew that there's an ankle boot? Is it a shoe? Is it a purse? Full stack is what you mean. Oh, got it. I'm an omni stack. I do everything. Who's your dentist? I need my teeth that straight. Ah, yeah. I did a lot of orthodontics. I've done a lot of orthodontics, you guys, over the years. A lot of braces. A lot of braces. So we ask the model what it thinks the answer is with the forward pass. Calculate the error. We know what the actual answer is, so we know the answer is actually a shirt. Even if it guesses that it thinks the answer is a boot, we tell it, no, it was actually a boot. Collect the derivatives of the error with the respective to the parameters, which is the back propagation for the gradients. We saw that in previous section, right? And then we do an optimization using those gradients that we calculated. And then it's just using gradient descent. It's a fancy term, right? It's a fancy term. For more detailed walkthrough of this process, check this video out on back propagation 3 blue 1 brown. Should we watch that, you guys? I think we might want to watch that. So tomorrow what we'll do, we'll get into actually training our model. That's what we'll do tomorrow. You know Spring Boot with Java? Yeah. Do I wanna? Am I glad that I know it? No, I'm not. Oh, Steven, did you hear about Claude benchmark fraud? No, tell me more. Torva, tell us about it. What happened? Let's watch 3 blue 1 brown for a little bit, you guys. Let's walk through it.
The hard assumption here is that you've watched part 3, giving an intuitive.
It's pretty long.
Algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the mantra to regularly pause and ponder certainly applies as much here as anywhere else.
Wait till you hear about the stochastic gradient descent. Yeah, I like that. I do that. That's my favorite one. I like that one. That's the one I personally implemented and use on a regular basis when I write my own custom AI from scratch. That's the one. I like that one, right? What is stochastic green? It means random. If you heard the word stochastic and you think it sounds like a cat because of the cat part in it, maybe you're right. I don't know. The cat is kind of random though, isn't it? Why is it stochastic? Why couldn't they just call it random? You don't like it when things always mess up on your words with a lot of typos. Hey, no, well, I do that all the time too. Kind of hard to type. Got a kid crawling on me using a voice text. Oh, no worries. Syntax seems familiar.
Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of networks, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function.
So the cost is sort of a array of the losses, the average of the loss. Is that right? Yeah, exactly. So many unnecessary, I know, right? So many the fancy words. There's so many math words in there. Just call it random.
And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is a L-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on.
That's right. I always say you don't need to be good at math to be a good programmer. In most cases, yes. However, when it comes to artificial intelligence, it's kind of nice to have some math in there. It's a little bit nice to have some math.
Let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that.
Wait. I need to unwind. I need to go backward. Sorry, I was like paying attention to Torva. Hold on. Torva. Okay, 1 second, Torva. So you said Claude got a benchmark, didn't manage to find the answer, analyzed the question instead of it realized its benchmarking question coded a decryptor for the answer since the answers are not decrypted. Instead of solving the question, it scanned every benchmark test and found the answer. Oh, so it found the answer instead of calculating the answer for the 12 questions. It revealed when Anthropic was reviewing the results Oh, well, was that a mistake or was that on purpose?
So the activation of the previous neuron is AL minus 1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or ReLU.
Okay, so we got a question there.
For...
How did you build your AI in the past, by the way? What kind of AI? Neural networks? Yes, so I've done a full from scratch using Python and from scratch using JavaScript and Rust. Then I did one in NumPy as another. And that was one that we did last year on Stream Live. Both kind of mean it not good for actually benchmarking. It kind of funny that it scanned every benchmark available online, made a decryptor for the answers. It did. It failed actually. Oh, okay. I kind of get it. All right, 1 second, you guys. I have to do something real quick. The timer is going off. 1 second. BRB. Okay.
For us, if we give a special name to this weighted sum, like z, with the same superscript
yes.
as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute z, which in turn lets us compute a, which finally, along with a constant y, lets us compute the cost. And of course, AL minus 1 is influenced by its own weight and bias and such. But we're not going to focus on that right now. Now, all of these are just numbers, right?
Yes.
And it can be nice to think of each one as having its own little number line.
Do you actually understand this math? Yes.
Understand how sensitive the cost function is.
I fully understand this math. 100%. This is like really easy. This is like the easiest part of it. They haven't even done... is this sigmoid right here? Is this an activation? I've written my own sigmoid before. Non-linear function, right? What did I click on? Hey, Fatty, good to see you. Welcome on in. Happy Tuesday. We're wrapping up stream. We've got a couple minutes left, and we're going over the 3 blue, 1 brown, the deep learning part, which is going to be mostly the backward propagation. So here's the cost. I'm barely in calculus AB. Hey, it's okay. You don't really need to. It's actually pretty straightforward. There's a lot of variables that are floating around here. All right, there's a lot of variables. All you got to do is put a number in. So you see right here, there's a number like 0.48 and a number 0.66. Just put a number where all these variables are, and you'll be fine. Just a number where the variables are. All right, you guys, we got 1 minute left. We got 1 minute.
Wait, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL.
Mm-hmm.
Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C.
It's the chain rule. Check it out. We just talked about that.
So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are. Because now we're going to compute the relevant derivatives. The derivative of c with respect to al works out to be 2 times al minus y.
You unwind it.
This means that its
You just unwind it.
is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of al with respect to zl is just the derivative of our sigmoid function.
Yeah, I knew that was sigmoid. I knew it. I called it.
And the derivative of zl with respect to wl, in this case, comes out just to be al minus 1. Now, I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that small nudge to the weight influenced the last layer depends on how strong the previous neuron is.
Sorry.
Remember, this is where that neurons that fire together wire together idea comes in.
Okay, we have to wrap up there, you guys. It was so good to have you here. I have to head out now. Jump over to the chat. So this was actually just a quick walkthrough. They makes it seem like it's a lot harder than it is. With all of these symbols, it's actually pretty straightforward. It really is. It's not that challenging. You can do this really easy with just a few lines of code, all the way forward propagation and backward propagation. 10 minutes, I know, right? Got 10 minutes. Been a pleasure. So good to see you guys. We're headed out. We'll be back tomorrow. We'll actually do this in PyTorch. We'll do this part tomorrow. That's the plan for tomorrow. We did it. We'll make it happen, you guys. It was good to see you. We're headed out now. Enjoyed seeing you guys. You are a what? I don't know what you're saying there, but I'm going to take it as a compliment. Thank you. Manic, good to see you guys. Heading out now. Thank you so much. See you then. We'll be back tomorrow. And we'll be doing this live. We'll be doing this actual thing. We'll make it happen. Gift. Gift. Thank you. Got it. Bye, guys. See ya. Thank you so much for joining. See you tomorrow. Bye, everybody.